Okay, welcome to lecture. We're going to pick up here in our final chapter where we left off last time, and hopefully, we'll be able to get through this chapter probably today. So, like usual, if you do have any questions, feel free to type them in, and obviously, we'll get those questions answered, and we'll hopefully, like I said, get through this chapter, and then that'll be it in terms of the lecture material. And then, like we've done before, we will have our exam during lab time. So we'll start during lab time. So you should go and take it, obviously, during that period of time. All right. So we were last speaking in this chapter about equilibrium. And remember, equilibrium really does deal with a specific type of reaction. And these are reversible reactions. And the one way that you can really recognize sort of reversible reactions is by the arrows that you kind of see. So when we have something like 2A plus 3B goes to, say, 4D in that case, right? And in these reversible reactions, we typically have these arrows a little better drawn than what I just did there, basically heading in both directions. So there's again, a forward direction where we usually assume that is going from reactants to products. There's also the reverse direction going from products back to reactants. And eventually it'll reach what we call basically chemical equilibrium. And remember that as we talked about last time, when we reach chemical equilibrium, again, doesn't mean that on the reactant side and the product side that we have exactly the same amount of each of those guys on each side. What it does mean when we talk about something that has basically reached equilibrium, what it essentially does mean is the rate of the forward reaction will equal the rate of the reverse reaction. And again, as we talked about last time, what that essentially means is quickly as it goes, say, to the right towards the products, those products will recombine and just as quickly go back to the left-hand side. And because the rate of those things basically occur at the same basically rate, like a better word there, or time, because they're going back and forth really at the same sort of rate back and forth, what essentially happens is wherever everybody is in terms of the reactants, in terms of the products, wherever they are in terms of their concentrations, later when you take 1B in terms of their pressures as well, they basically will be able to maintain where their numbers are. So for example, like maybe example last time, if the first guy ended up at 4 and 2 and the guy on this side was at 3, and say those are just made up sort of concentrations for everybody at equilibrium, what that means is once this reaches equilibrium on the left-hand side there, those guys will be able to maintain basically their 4 and 2 in terms of their concentration. On the right-hand side, they'll be able to maintain sort of the 3. And it's just because as quickly as they go one way, they come back the other way. So as we talked about, when you look at something that's reached equilibrium, for example, in a beaker or whatever it may be, again, it may appear to you sort of like the reaction's over, everything has stopped. You don't really see a lot of change occurring at that point. But as we talked about, if you sort of super zoomed in to the molecular level, you would see a lot of activity. You would see a lot of reactants going to products. You would see a lot of products going back to reactants. And this sort of back and forth is consistently happening at the same rate. So sometimes on the big picture, the macroscopic level, it sort of appears like not much is happening when something reaches equilibrium. But again, there's a lot of activity that's continuously occurring. It just may not look like much is changing because, again, everybody at that point is able to maintain pretty much where they're at. Now, one way that we sort of express equilibrium is through capital K, which is the equilibrium constant. And the equilibrium constant, which is K, is a constant value for a particular reaction specifically how that reaction is written, and also specific for the temperature at which that reaction takes place. The way we typically calculate it is to take the concentration of our products divided by the concentration of our reactants. Again, the little brackets there typically mean concentration. And usually what that means is molarity, which is our moles per liter, right? So we take our products or reactants. The other important part is when we do that is we do take the coefficient that we find in the balanced equation and we do incorporate that in. So if we were to write the expression for our reaction above, it would be the concentration of D, and we would take it to the fourth because of the coefficient, divided by the concentration of A, which we would square, times concentration of B, which we would cube. So again, important when you write the equilibrium constant is capital K. Small k is actually something else entirely, so you do want to make sure it's capital. And we do take usually the concentration of our products over our reactants. Now, we also sort of finished last time talking about certain things that are sort of not included when you write these expressions. And the things that are not included are things that are solid and pure liquids. So a pure liquid, again, pretty much remains constant in terms of its concentration. So something like water, for example, that's in the liquid state would remain constant, and you would not include it in the expression. Something that's a solid, like we sort of talked about as well last time, if it's a solid, it's pretty much, you could kind of visualize it like it's, just sitting there. So not much is happening with it. It's not really participating very much. So again, in order for it to participate, it would have to perhaps dissolve. And that would get us the two things that we do include in these. So we do include anything that's aqueous, so anything that's the aqueous symbol next to it, and anything that's a gas. So these guys do get included into the equilibrium expression. Things that are solid and liquid, we do leave out. And again, because they're really not participating or basically being involved in sort of what's happening in that equilibrium. K as well, a couple of things that we did talk about K. K has no units typically. It's just a number. But that number does tell us something. So if K is a large value, what that means is we would have mainly products, higher number of products than reactants. And that means that when we do reach equilibrium, we should mainly have products at that point being made. And vice versa, if we calculate K and actually given a K value and it's small, again, mathematically speaking, in order to get a small number, we need small products, more reactants. We mainly have reactants at equilibrium. And the value of K that's considered large is, again, that value of K greater than 1. Would be considered a large value, and obviously less than 1 would be considered a small value for our equilibrium. So the actual value of K, a lot of times, and again, a little bit outside of our class for the most part, but definitely if you get to 1B, you'll see it a lot. It does give you a lot of information about, sort of what's happening when we do reach equilibrium. And the last thing we sort of talked about systems at equilibrium is sort of the equilibrium constant. Again, it is a constant value. The only thing that will actually change the value of K, for example, if you look at a reaction. So if we looked at this reaction here, and if we said K was 25 at, say, 30 degrees Celsius, right? What that means is this reaction at 30 degrees Celsius will always have the same K value of 25. Again, no matter what ratio, I guess to say it better, no matter how much reactants you started with, no matter how many products you started with, if you started with some reactants, some products, you started with different amounts and different experiments. If you ran the experiment and you calculated K, it will always end up in this make-believe example here of 25. And that's sometimes hard to sort of for people to visualize. So I guess what I'm trying to explain here again is, for example, say in experiment 1, you had 4 of one reactant, 2 of the other, and you got 3 of the other. And then if you did another experiment where you started with 5 of this guy, the first reactant, and like 1 of the next reactant, and whatever it made on the other side. So, you can start with different amounts of reactants. You start with different amount of products. But as long as you keep the temperature at, say, 30 degrees, for example, the ratio of the products to reactants will always be the same number, or pretty close to the same number. Now, if you take that same reaction and you go, say, to 40 degrees Celsius, you will get a K value, maybe, again, just making it up, say, of 45 for that reaction. And what that means is at 45 degrees Celsius, if you keep it at 45 degrees Celsius, and again, you start with different amounts for different, say, experiments of your reactants and so forth, it will always come to the same ratio of about 45 for this made up example. So what we mean by if you change the temperature, you'll change the value of K. What we mean is in comparison between, say, temperature of 40 degrees Celsius and 30 degrees Celsius, the K values will be different. But if you maintain the temperature at the same temperature and you do a whole bunch of different experiments with different amounts, it will maintain its K value for that particular temperature. But if as soon as you change the temperature, the K value will change. But then if you keep it, say, at 40 degrees Celsius, it will be able to maintain that same K value. So that's sometimes hard for people to understand when they deal with equilibrium sort of problems. And again, you'll see more of it in 1B, but the value, since it's called an equilibrium constant, should give you a constant value regardless of how much you start with. So people always think, well, I started with twice as much of the first guy than I did in the second. It should come out to a different number, but it won't. So again, the only thing that will affect it will be temperature, and that's where you'll see it. And that's why when you do see a K value written for an equation, it is based specifically for that reaction, exactly how it's written, and at that specific temperature. So if you reverse the reaction, the K value will change. If you change the temperature, the K value will change, but it will maintain that K value at that temperature as long as you don't do anything to it in terms of temperature. So writing our equilibrium expression here for this one, where I think is where we left off, again, we would do our products divided by our reactants. Now, when we look at this, this is again what it was referred to at the end as a heterogeneous equilibrium. And heterogeneous equilibrium, much like heterogeneous mixtures, again means that you have things in different phases. And here we have some solids, we have some gases and so forth. And that's different than, say, a homogeneous equilibrium, which we talked about also at the end. Homogeneous, just like the solution means it's the same throughout. So in a homogeneous equilibrium, everybody's in the same phase. So here we would do our products over reactants. So we would take our product, which is our O2. Again, we would cube it because of the coefficient. But now on our product side, we have a solid, which would not be included in the equilibrium expression, over our reactant, which happens to also be a solid. So again, we wouldn't leave it in the equilibrium expression. And this would be our correct K value for it. Again, sometimes referred to as Kc because C means concentration. So we're dealing with the concentration here. Any questions on how to write that equilibrium expression? So remember, anything that's a solid or liquid, we do not include into the expression. And again, that leaves you pretty much gases and aqueous. And I think we might have touched upon as well, since the only thing here is really a gas, we could write a K, what's known as P value for it, which would be the pressure of O2 cubed. And this would be the partial pressure, which is another way an equilibrium value is sometimes written, especially where gases is involved. Partial gases, no, that's partial pressure. Okay, so All right. Any questions on equilibrium? All right, so we're going to then talk about, we'll take one more. Let's take a look at this one here. Again, we're going to do our products over our reactants. And when we look at it, our products are both aqueous, so they both would be included. So it would be K is equal to the concentration of calcium times the concentration of F minus. Again, we would square it because of this coefficient. Technically, the coefficient here is 1, which is why, like usual, we don't really write 1, but it's assumed to be 1 in this case. But now when we get to our product side, we do have a solid. So again, it would not be included in the equilibrium expression. And this guy here would be our equilibrium expression there, which is what they have boxed on the bottom. So again, always products over reactants, and just eliminate anything that's a solid or a liquid. Okay, so what we're going to talk about now is what's known as Le Chatelier's principle. And Le Chatelier's principle is basically what happens when some type of change occurs to a system that's at equilibrium. A change, or sometimes they're referred to as a stress. So the idea here is basically we have a system that's at equilibrium. So we got this system that's at equilibrium. And what happens is you sort of add a stress to the system. And much like anything else, it stresses it out. And it essentially what it does is it messes up the equilibrium. So you add the stress, sort of, for lack of a scientific word there, messes up the equilibrium. And what that means is because of whatever you just did, you no longer have the rate of the forward reaction equaling the rate of the reverse reaction. And what's going to happen is the system wants to get back to equilibrium. So the system is going to want to eventually get back to equilibrium. And in order to do that, there's really 3 options that will sort of occur. It may have to shift to the right, which essentially means that you need to make more products, right? Right-hand side of the equation, right, is products. Right, left-hand side is reactants. It may also need to shift to the left, which means it's going to, like I just mentioned there, make more reactants. And there's a third case that could occur when we talk about sort of Le Chatelier's principle is there actually could be no change that occurs. Yeah? So there is a situation where even though you did something to this equilibrium, it's not going to cause any type of change to occur. So we have a system that's at equilibrium, which again means the rate of that forward reaction is going to equal the rate of the reverse reaction. We add the stress to it, messes up that sort of situation. It's going to either shift to the left, going to shift to the right, or may have no change. And what that's going to allow to happen is the system will again reach equilibrium. So this is the idea behind sort of Le Chatelier's principle. Everything's good, everything's happy, they're at equilibrium, they're going back and forth at the same rate. You do something to it, it messes it up, and then you're able to regain equilibrium by going to the left, going to the right to do that. So when we talk about stresses, there are certain types of stresses that we could do. And the first one, as we'll talk about, is concentration. And as you'll see, you can pretty much either add or remove concentration. Those are kind of your 2 options. There's also volume and pressure. which usually deals with gases, which means you can either increase one of them or both, or decrease volume or pressure. There's also temperature, which can affect the equilibrium. So you could either increase the temperature or decrease the temperature. And sort of the last thing that people sort of think about when they're talking about adding stresses to a system at equilibrium is you could add a catalyst. And if you remember, as we talked about, I think as well last time, a catalyst is something that's added to a chemical reaction. And basically the whole point of it is to speed up a chemical reaction. So a catalyst is not considered a reactant, it's not considered a product, is there simply to sort of facilitate that reaction happening faster. So as we talked about last time, the way it's able to do that is by lowering that activation energy. So if you remember, right, the activation energy is the hill that the reactants has to climb to get to the other side to make products. And one way that it's able to do that faster is when you add a catalyst. It provides a lot of times a more efficient way for things to come together. And ultimately what that does is lower the activation energy. So it's just they don't have to climb the giant hill to get to the other side. They have a much smaller hill, allows them to get to the other side faster, and thus the reaction occurs a lot faster. So we're going to talk about each of these and sort of the effect that it has on systems at equilibrium. So I think we're going to start with concentration, I hope. Yep. So we're going to start with concentration. And when a reactant or product is added to the equilibrium, it will result in it shifting away. So a good way to remember it is add away. Yeah. AA, so add away. So if you add some reactants, you will then make the equilibrium go towards the product, so the right-hand side, away from the side you added. If you added more products, which is on the right-hand side of the equation, it will force the reverse reaction to occur, and you will make more reactants, and it will shift to the left. When we remove a reactant or product, it will shift towards it. So removing is different. When you remove, it shifts towards it as opposed to away. So if you remove a reactant, it will go shift the equilibrium to the left towards the reactant side. If you remove a product, it will shift it towards the product side. So when we talk about sides, and in reality, to be honest with you, if you had a solution, there is no kind of left-hand side, right-hand side. So when we talk about which side you're adding it to, you're not really adding it necessarily to kind of physically, I guess, you sort of are, but you can't really visualize it. But when we talk kind of left-hand side, reactant side, product side, we want to look at the equation basically. And on the equation, you'll be able to see these things either as a reactant or as a product. So again, when we think about adding something that's a reactant, it should always be on the left-hand side of the equation. And that means that it should shift away and go to the right-hand side. And vice versa. If we remove like a product, which is on the right-hand side of the equation, it should end up shifting to the right-hand side of the equation. So adding is pretty simple. If you want to add more of something, you essentially just go to the shelf, pick it up, and dump it into like your beaker, right? It's just easy to add something. Removing something that's, say, in a solution is oftentimes a little bit harder to do. You can't just reach in with your hand and pull something out of a solution. You should never do that, by the way. So how do we remove things from a solution, right? Well, there's really two common ways we can remove things from a solution. We can make a precipitate. PPT is a precipitate, which essentially means we add something to the beaker that's not part of the reaction. So you don't see it actually on the reactant side. You don't see it on the product side. But when you add something to the solution, something on the reactant side or something on the product side will actually react with whatever you're adding. And when it reacts, it's going to make a precipitate. And a precipitate, right, is a solid. And as we talked about earlier, one of the things that are not included in the equilibrium expression are things that are solid. So when we make this solid by adding another solution to it, we are essentially reaching in and grabbing out, for example, an ion. So for example, let's say you had a beaker that had silver ions floating around it, and along with some other stuff, but we're just gonna concentrate on the silver, and we'll just say, hey, we have some silver ions in a reversible reaction, whatever it makes on the product side, right? Now, if I take something like, say, sodium chloride and I add it into this beaker, right, the silver ions and the chloride ions coming in will come together to make silver chloride, which is a solid, right? And what we would see is on the beaker, a not red solid, but you'd see a white solid being made, right? And that white solid is the silver chloride. But in terms of Le Chatelier's principle, what we're doing is essentially taking our silver ions, which is on the left-hand side of the equation, and we're basically removing them. Because now those silver ions are tied up in the silver chloride, which is a solid. They no longer will actively be able to participate in the equilibrium because they're in a solid. And what that's going to cause is this equilibrium to shift towards the silver, to the left-hand side, as a result of that. Another common way you could remove something from a solution, which is a little harder to see. Now, making a precipitate is typically very easy to see because you'll actually see the solid in the solution. But another way that we can sometimes remove something from solution is when H plus and OH minus come together, and that makes our good friend water. And water is a pure liquid, which, if you remember, also is not included in the equilibrium. So this oftentimes happens when you have kind of like an acid or a base involved. So usually if you had H plus in the equation, you added something with hydroxide OH minus, you're going to make water. And essentially what that would do is remove the H plus from the equilibrium. Or if you had a base, something with OH minus in it, you may add an acid to it, which would then remove the OH minus. This one, again, visually a little bit harder to actually see because you can't really see, oh, I just made more water, right? You really won't physically sort of see the water being made. But if you understand the equation and the hydroxide, the OH minus and the H plus and where they're at, you can understand that you're actually removing something. And you won't necessarily visually be able to see the water part being made, but you may visually be able to see the equilibrium actually perhaps change colors, for example. Now, sort of a basic sort of way of thinking about it is like your classic teeter-totter seesaw type of deal. So you got your nice stick figures there, 101. There we go. And this system is at equilibrium. Everything's good, for example. We'll call the left-hand guy the reactant. The right-hand guy is our products. Now, if we added more people to the right-hand side, what's going to happen is that's faces on stick figures. That's impressive. So we just added more here. We obviously messed up the equilibrium, right? Now to fix this, we would need more people to actually get on the left-hand side. So what's going to happen is we added to the right is going to shift away to the left-hand side to fix the problem. And eventually it will come back to equilibrium. And at that point, we would have something here. Back to equilibrium again. So this is what happens when we, for example, add something. We always add and then we'll shift away. So in this case, we added to the right. It will shift to the left, which means we need to make more reactants until, again, it's able to achieve equilibrium. Same thing if we took our guy here to start with, and we're at equilibrium. Again, this guy will be our reactant. This guy will be our product. And let's just say the guy on the right hops off and he decides to hop off of the seesaw. What's going to happen in that case is this situation. And to fix this, obviously what we can see is we now need more people to the right. So it's actually going to shift towards the side we removed it from. And when it shifts towards that side where we removed it from, we will once again reach equilibrium. At this point. So again, this would be when we remove. Any questions on adding or removing concentration? So add away. So whichever side you add it to, will go to the other side. It will shift to the other side. So again, if you add more reactants, it will shift to the right to the products. If you add more products, it will shift to the left to the reactants, and vice versa for removing. It will go towards the side. So if you remove reactants, it will go to the left, and if you remove products, it will go to the right. So let's talk about what happens when we change volume and pressure. So volume and pressure are essentially tied together. And volume and pressure, you may remember, oftentimes we'll deal with gases. And our good friend Boyle, right? Boyle said that as the pressure goes up, volume goes down, and vice versa, right? The pressure goes down as the volume goes up. So when we think about volume and pressure, oftentimes they are tied together. So if we increase the pressure, that means that the volume is going to go down. And what that means is there's a much smaller space for these gas molecules to fly around in, right? So if we decrease the volume, these gas molecules are now very close to one another. And what's going to happen is that's going to cause more collisions, right? And that's why we do see the pressure start to rise. So to fix that, what we need is in the smaller volume, we actually will need less gas molecules. So the idea here, if you want to think about it this way, is when you do this, you decrease the volume, the pressure starts to rise. Right? So what we want to do is kind of bring the pressure back down. So in order to bring the pressure back down, what we need to do is shift to the side that has less gas molecules. So we want to shift to the side with the least number of gas molecules. Now, in this case, you can't really determine, is that the left-hand side, is that the right-hand side? It is reaction dependent. So you do have to look at the reaction and figure out, which side has more gas molecules on it and which side has less gas molecules. And you can do that by simply looking at the coefficients and adding up all the ones that have G's next to it. Now, the opposite is true if we take the pressure down and the volume up. What's going to happen in that case is now our gas molecules have all this space to fly around in. And when the volume increases, the pressure will start to decrease. So what's going to happen in that case is the pressure will start to go down. So what we want to do is kind of fix it by bringing it back up. So the only way to bring it back up in that situation is we will need more gas molecules to fill this area. And it will shift to the side with more gas molecules. So again, you would have to look which side has the most gas molecules in that sort of situation. So personally, when I think about pressure or I think about volume, I personally always sort of think about it in terms of the volume part. And when you think about it in terms of the volume part, it's pretty straightforward. Bigger area, more gas molecules. Smaller area, less gas molecules. So let's just look at sort of an example here. Let's just say we had 3A plus 2B, and we have, we'll do 3C over here, okay? All right, I'm going to give you a couple different scenarios here based on the last couple of things we're talking about. And you take a minute or so and try to figure out which way it's going to shift. So what you want to know is, will it shift to the left? Will it shift to the right? Or will there be no change? So let me just give you a few different options, and then you can think about it, and then we'll talk about it. Let's say in this case, we added more A. We removed C. We removed B. Let's say we increase the volume, and let's say we increase the pressure. All right, so take a minute or two and think about it. For each of those things to this system at equilibrium, will it cause a shift to the left? Will it cause a shift to the right? And will it be no change? And we'll talk about it in a minute here. All right, so let us take a look here and see. So we are in the first one here, adding more A. So again, you do kind of want to look at your equation here. And this is sort of where we could kind of think about left side, right side, okay? So when we add more A is on the left-hand side. And when we add, it goes away. So what should happen is it should actually shift to the right-hand side in this case. And it's kind of like what we were talking about last time as well. When we add more A in this case, what's going to happen is we have a lot more A that can react with B, and that's going to cause the forward reaction basically to kick off. And that's why we say that is shifting to the right in that case. As we talked about, right, the concentration of A will go up, which means it will react with B, which will go down. And then C in this case should increase as we're making products. Now, when we remove C, C is over here on the right-hand side. And when we remove, it will go towards the side we removed it to. So in this case, by removing C, which is on the right, it will actually cause the equilibrium to shift to the right-hand side. So what's essentially happening in that case is we essentially will have kind of the same situation. By removing C, which is a product, we will then have really more reactants, and the equilibrium will be messed up. So to fix that, those reactants are going to try to equalize that. that removal of C, and it will shift to the right. Any question on those first two? Now, same thing as well. If we remove B, which is over here on the left-hand side, again, when we remove, it goes towards the side we removed it to. So that's going to cause the equilibrium to shift to the left, heading towards the reactant side. So again, here, there's sort of a void on the left-hand side, right? So we removed it. So kind of in our go back one. There we go. Kind of our teeter-totter thing here. Again, when we remove it, the teeter-totter will come up. So to fix it, it's got to come back down, if you want to think about it that way. So in the case of B, our teeter-totter would kind of do that deal, our seesaw. So to fix it, we need more people to come back to this side to bring it back down. Now, in terms of our volume over here, when we increase the volume, again, volume and pressure are related, which means the pressure will decrease. But when we think about volume, more volume, we need more gas molecules. So it will shift to the side that has more gas molecules. So again, that's dependent on the reaction. So if we look here on the left-hand side, they both are G's. And really simply, all you need to do is add the coefficients. So we have 2 there and 3 here. That gives us 5 gas molecules on the left-hand side. When we go to the right-hand side, this is a G as well. We have 3 gas molecules on the right-hand side. That means in this particular case, when we increase the volume, the equilibrium will shift to the side that has more gas molecules. So in this case, it will shift to the left. Any questions on that particular one? And lastly, we're increasing the pressure. So increasing the pressure, again, will actually make the volume decrease. So we're going to have a smaller volume. So remember, when you have a smaller volume, you need less gas molecules. So again, looking at the same reaction as below, we again will still have the 5 gas molecules on the left, the 3 gas molecules on the right. So that would cause the equilibrium here to shift to the right-hand side. Any questions on any of those sort of shifting or anything like that? So that is concentration, that is pressure and volume, which again, oftentimes are tied together, and really only gas is sort of affected with those sort of shifts. And again, personally, I always look at the volume. It's just an easier way to remember it, as long as you understand the pressure and volume relationship, like in Boyle's law. So if you just think about volume, big volume, more gas molecules, small volume, less gas molecules. And that's a really good way to sort of remember, that sort of change. So as we can see here, the volume is suddenly decreased. So we do need to shift to the side that has the least number of gas molecules, again, because that's going to offset the pressure that's going to cause. So why high pressure causes equilibrium on the last one? Yeah, let me go back there. Okay. So in this case, when we have a high pressure, what that means is the volume is going to be small. So over here in this smaller volume, if you do nothing but leave everything the way it was and that volume decreased, what's going to happen is the pressure is going to start to go up and go up and go up, because as you can see in the picture on the left there, we have a lot of gas molecules in a very small area, right? So that's going to cause a lot of collisions and the pressure will continue to rise. So because the volume itself is not going to readjust again, the only way to get the pressure sort of back down, if you want to think about it that way, is we need actually less gas molecules in that smaller space. So if by it shifting to less gas molecules in that smaller space, say just 1, for example, that 1 gas molecule is going to cause the pressure to start to decrease because there's less gas molecules in that very small volume, and that would cause it to have less collisions and the pressure will start to decrease in that particular case. So it is sort of reaction dependent. So when we look at this particular reaction we're dealing with here on the bottom left, when we count up all the gas molecules on the left-hand side, there's 5, and all of them on the right-hand side, there's 3. So in this particular reaction, to get us to less gas molecules, the equilibrium would have to shift to the right, because that would make more products, and technically we would have less gas molecules that are flying around. So again, the volume aspect of that is really sort of the easier way, I think, for most people to remember it. Again, large volume means smaller pressure. To fix it, we need to put more gas molecules in there to bring the pressure back up, and vice versa. When we have a small volume, that's a larger pressure. So to kind of fix that large pressure, we need to bring the pressure back down. So we need less gas molecules in that space, which would cause less pressure. Other questions? And that's what we see here. So this is decreasing the volume, which would cause this pressure to increase. And the reaction we're looking at here is N2 plus 3H2 goes to 2NH3, right? So in this case, the pressure is going to go up because our volume went down. So we need to go to the side that has the least number of gas molecules. So when we come over here, there's 3 gas molecules there, and one more makes 4 gas molecules. This guy is 2 gas molecules. So we would expect this equilibrium in that case to shift to the right, which is the smallest number of gas molecules. And vice versa, if we increase the volume, the pressure would start to go down. So to bring the pressure back up, it would need to go to the left in this case, which has more gas molecules over here. By the way, if I added NH3 and I removed N2 in this reaction, which way would it go? Take a second and think about it. All right, so when we look at this here, we have adding more NH3. So NH3 is on the product side. Remember, when we add, it shifts away. So it's going to shift, in this case, to the left-hand side, away from the side we added it to. And if we removed N2, so N2 is over here on the left-hand side, it will go towards the side we removed it from. So it actually will also go to the left-hand side in this case. Any questions on those two? So again, an increase in the volume, it will shift in the direction that increases the pressure, and we'll get that. Now, let's talk about temperature and how temperature affects equilibrium. As we talked about earlier, temperature is really the only thing that affects the actual value or number of K, like we talked about. If you change the temperature, the actual value at 40 degrees Celsius for K will be different than, say, 75 degrees Celsius K for a particular reaction. Now, temperature works the same way as concentration, which means just like concentration, if we increase, it will shift away. And if we decrease, it will shift towards it. So when we talk about increasing temperature, decreasing temperature is pretty much that. Either, you raise the temperature, you warm it up like in a water bath or something like that, the test tubes. Or maybe you throw it in an ice bath, right? Which has ice, it cools it down. So when you increase the temperature or decrease the temperature, it will shift away just like concentration, or shift towards it. The main thing that you have to determine, though, for the actual equation is what type of reaction are you dealing with? And what type of reaction, what we're talking about is the reaction exothermic, or is the reaction an endothermic reaction? So exothermic, again, means that heat and energy is released or produced as a result of it. And when we think about exothermic reactions, the heat and energy is thought of as a product, which means if you were to slap that into the equation, it would be on the product side. We also talked about heat and energy and exothermic throughout the semester, and there's a couple other ways you can identify heat and energy by Q, right? And that means you will get a negative number. And we also talked about delta H, which is the enthalpy. And that's a very common way that reactions are basically told to you as being endothermic or exothermic. They give you the delta H value for the reaction. The number is really not important. The only thing that's important is actually the sign. So if you see a negative number with a delta H value, for our purposes, you really don't have to do much with it other than know, oh, it's negative. So that means that this reaction is exothermic. Endothermic is the opposite. Heat and energy is thought of as a reactant. And it would actually be written into the formula on the reactant side if you put it in. And also for endothermic, if we calculate Q, that's a positive number, and delta H would also be a positive number as well. So in these type of things with Le Chatelier's principle, typically you'll have some type of information that will help you decide whether or not a reaction is exothermic or endothermic, especially if it's more of a textbook type problem. It will give you most likely a number like this, or it may just tell you straight out, this is exothermic, this is endothermic. So when we look at these guys for an exothermic reaction, like I wrote up there, A plus B goes to C plus heat, right? The delta H would be negative. And that means in an exothermic reaction, if you increase the temperature, it would be like adding a product, which means the equilibrium should shift away and go to the left-hand side. If you decrease the temperature, that would be like removing a product, which means it should then shift towards it and would go to the right-hand side. Now, if you had the endothermic, it would be the opposite. You would have heat plus your reactants. And if you increase the temperature, again, in this case, because it's endothermic, delta H would be positive. It would be like it'll be like adding more reactants, so it will shift away. It will go towards the product side. And if you decrease the temperature, it will be like removing a reactant, which means it would head towards the reactant side. So in terms of temperature, it's important to somehow figure out endothermic or exothermic. And like I said, if it's not an experiment, in an experiment, you can kind of figure it out without being told, usually, in most cases. But usually in a book, you'll be given some type of information that will allow you to do that. Either, again, you'll be given the delta H value, or you'll actually see the heat written into the equation. You may even see a value for heat. Remember common units of heat and energy, joules and calories, right? Like we talked about with specific heat. So sometimes they may just even write into the equation like A plus B goes to C plus 112 calories or something like that, right? And again, the number doesn't really matter. The location of the number is important. We do see it's on the product side, which would tell us it's exothermic, as opposed to if you had sort of the same reaction where you took 112 calories plus A plus B goes to C. Here, the energy sort of values on the reactant side, which would be telling us is being absorbed and be considered an endothermic reaction. Any questions on temperature here? Let's see here. All right. All right, so let's take a look at this one, and we'll just do a whole bunch of sort of examples off of this one here. We're just going to make this up, and I'm not sure if it's right or not. We're just going to say the delta H value here for this reaction is negative. All right. So let's see what happens here. Yeah, I'll go back here in just a second here. I think about what I want to kind of put on there. All right, so we're just going to use the next example and kind of do a lot of the stuff that we've been talking about, so you can kind of maybe figure out what's going to happen with the equilibrium here. So let's take a look here. So let's say that we added O2. Let's say that we removed CO2. Let's say that we increased the temperature. Let's say we decreased the pressure. And let's say we added more CO. All right, so take a couple of minutes here and a minute or so and try to figure out what's going to happen in each of these cases. Will it shift to the left? Will it shift to the right? Or will there be no change in this case? So think about what will happen in each of those cases if we separately did all those things. Okay, so let us talk about what's going to happen in each of these cases. So again, going under the assumption that this is negative. That first tells us that this is exothermic. And that tells us if we were to write the energy in, it should go on the product side because it is exothermic. So that's going to help us with some of these. Let's start with the first one here. We're adding CO. CO is on the product side, which means add, it goes away. So we add it to the product side. That should cause the shift in equilibrium to go to the left-hand side. Now we added some O2. Again, same thing. We added O2. Again, add away should also shift it to the left-hand side. We removed CO2, so CO2 is over here. And when we remove it, it actually will go towards the side we removed it from. That will cause the equilibrium to also shift to the left. Now, we increase the temperature. So again, this is why it's important to figure this part out. Because it's exothermic, what that tells us is heat is on the product side. And remember that temperature works the same way as concentration. So increasing the temperature would be like adding to the right-hand side, which means it should also shift to the left-hand side there. Oh, I picked all left, so see how we did on the last one here. Maybe we'll go the other way. The last one is we're going to decrease the pressure. So that means pressure is going to go down. The opposite of that is true. That means volume will go up. So again, sometimes the best way to think about it is with the volume aspect. Bigger volume means more gas molecules, right? So we do want to count. On the left-hand side, we have 2 gas molecules, coefficient. Right-hand side, they're both gases. There's 2 here and 1 here, which gives us a grand total of 3 gas molecules. So I did get at least one going the other way. It should, in this particular case, shift to the right because it has more gas molecules. Any questions on that there? Okay. All right, so here is another sort of example here. So this guy here is endothermic, which means if we decrease the amount of H2, so we'll just do it this way. Endothermic means that heat would be written in over here. And in this case, if we increase the temperature in this case, because it's endothermic, that would be adding heat to the left-hand side. That should cause it to shift away, add away, right? So it should go to the right-hand side in this case. We did the opposite and decrease the temperature. That would be like removing our reactant over here. And when we remove it, goes towards the side. So again, in this case, should shift to the left. So, and it's asking in this case, how many of the following changes would decrease the amount of hydrogen gas produced? So what we're asking here is basically how many of these things would cause the equilibrium to shift to the left, okay? So the question is, how many things will cause the H2 to basically decrease, which means we want to shift the equilibrium to the left. So if we go through it, if we added more H2O to this, that would be like adding over here, which means the equilibrium would shift to the right, right? So if we did that first one, it would shift it to the right, which would actually make more H2. So that definitely wouldn't do it. If the volume of the container is doubled, so in this case, the volume would go up, the pressure would go down. So we would want to shift to the side that has more gas molecules. So on the left-hand side, there's 2. Right-hand side, there is 1 and 3 make 4 gas molecules. So if you did number 2 on the list, that also should cause the equilibrium to shift to the right, which would make more H2, which is not what you're trying to do here. Now, if we do number 4, where excuse me, we remove CH4 from it, CH4 is on the left-hand side. So when we remove it, it's going to shift towards the side we removed it from. So number 3 would actually cause the shift to occur to the left, which means we would actually make less H2. So that is the one that actually will do that change. And lastly, the temperature is increased. So as we just talked about up here, if we increase the temperature, should cause the equilibrium to shift to the right, and that would make more H2. So in this case, only one thing would cause less H2 being made, and it is number 3 here on this list. That is the thing that will cause less gas molecules in terms of H2. Any question on any of that stuff there? Okay. Now, one last thing in terms of Le Chatelier's principle is a catalyst. And if you add a catalyst, if you actually add a noble gas as well, by the way, to an equilibrium, they will cause no change. So that is a way you could get no change to occur. There's also another place where commonly a no change could kind of occur. Again, a catalyst will just speed up the reaction. It will not cause it to go left or right. It will just sort of occur faster. But for example, let's say we had 2A plus B goes to 3C, right? And let's say here we increase the pressure, right, in this situation. Now, when we increase the pressure, as we've been talking about, we know in terms of volume, what that means is the volume is going to go down. So that's a small volume, which means we need the least number of gas molecules. Yeah? Now, on the right-hand side, when we count up the total gas molecules, there's 2 there and 1 there. That is 3. When we look on the product side, that is 3 gas molecules. Yeah? They call that a tie, right? There's 3 on each side. So in this particular case, this would be a no change as well. Again, because the left-hand side has 3 gas molecules, right-hand side has 3 gas molecules, there really is no side that is larger or smaller. So that's sort of a third way you could commonly get like a no change answer. So the 3 common ways sort of for a no change answer, most common one is you added a catalyst. Again, will not cause any type of shift left or right. It will be no change. If you add a noble gas, because noble gases are chemically inert, they can bounce around in there and really have no effect on the equilibrium. And here at the bottom is sort of the third way that you can commonly got a no change. Is a situation where you have all gases, but you have basically the same number of gases on each side. So again, there's no greater side or lesser side. You basically have the same amount. Any questions on sort of Le Chatelier's principle there? So what we have on the screen here is what we kind of talked about as well earlier. Again, the value of K, if it's larger than 1, and as we talked about last time, the reason why we want is sort of that number is because you're taking your products divided by your reactants. So again, if you had an equal amount of both of those guys, you would end up with 1. So anything above that would mean you kind of tipped it to the product side. Anything less than 1 means you kind of tipped it to the reactant side. And again, as we talked about, if you had a really large value of K, and there are some things that have a very, very large value of K on the order of like K is equal to times 10 to the 30. I mean, that's pretty much meaning that although it technically is still a reversible reaction, it's pretty much all going in that direction. But it's still reversible. So even though almost 99.9% of it is going to the product side, there still is a smidge of it coming back the other way. And that's why it says, going back the other way to the reactant side, that's why it says that it essentially goes to completion, because it is still ultimately an equilibrium reaction. So it still has the ability to come back the other way. It may just mean that everybody on the left-hand side, the reactant side, their concentrations are like times 10 to the minus 18, like barely anything there, but there's still technically something there. And as we also talked about, if we have a small value, again, what that means is as we go to Equilibrium, we would mainly have reactants for the same reason. The only way really to get a small value when we take products over reactants is you need to have a bigger number on the bottom, right, than your top. So small number on top divided by a big number on the bottom gives you a small number. And again, what that means is the equilibrium lies to the left, that you mainly have reactants at equilibrium than products. And just like when you can have a really big value of K, you can actually have a really small value of K. So again, say you had a K to the times 10 to the minus 25. That means essentially this reaction is not happening at all. It's pretty much all staying here on this side. But if you did the calculation, you got a smidge of these guys being made, on the product side, but pretty much is staying there on the reactant side. All right. So let's see here. I think we'll stop here, give us this last little bit to talk about, at least on Wednesday, give us something to talk about for our last lecture. So we'll finish up the last part here, which is some calculations, so we won't get into that right now. So we'll finish up the rest of this chapter on Wednesday. Any questions on stuff we've been talking about first off? Okay, so let's talk about what's kind of left here. We're going to take the exam. It's going to be open in about 15 minutes at 12. You should go and take it exactly at 12 so you don't run into any problems or anything like that. So just go take it. Like normal, reminder, there are different versions and different questions. So make sure, you have your answers on your test and all that good stuff. Make sure that you upload your work in an appropriate amount of time. I think you got like 30 minutes after the exam. That should be plenty based on what I'm seeing. It shouldn't take you really any longer than that. So make sure that you do upload it within that 30-minute period. Otherwise, again, you may not get credit for any of those questions. So it shouldn't take you all day. A reminder that the answer that you submit online does need to match the answer that you submit for your work. So again, if they don't match, or magically after you submitted your online exam, you got the right work and answer on your paper, again, you will not get credit for that either. So make sure that it does match and all that kind of stuff. Remember, there's only some certain questions that you do need to show work for. So make sure that, you do show the work that includes all the setup, the units, and all the correct sig figs for each of the questions, because again, it's a computer answer. Please follow the instructions on each of the questions as to how to enter it, so you don't have any problems. Follow the format like it shows in each of the questions as to how to properly enter it, and you shouldn't have any problems, hopefully. A reminder again that sometimes it will cut off a 0 at the end and stuff like that, but it should be okay. But do follow the specific instructions for each of those things. Any questions on the exam? So that will leave us Wednesday of this week, where we'll finish the last little part here. We will then do the last experiment, which will be Le Chatelier's principal experiment, which I think is 24. Again, 25 is really more of a checkout experiment, so we're not going to worry about that one. But you'll do experiment 20. What are we at there? 24, I guess, right? And you should be able to hopefully do that now with our talk here. And after Wednesday's lecture, you should be able to finish the post-lab questions on those as well. And then that will leave us 1 week from Wednesday, which is the final exam. Yeah, so the final exam is comprehensive over all the chapters. I believe it is 1 week from Wednesday, and I think it starts 10-ish in that ballpark, 10:30-ish. It's on the syllable. It's on the syllabus as well. When does it start? Yeah, the lab will be due Wednesday, so we'll start the lab Wednesday, and it'll be due Wednesday. You pretty much could do the most of the lab. There's still some post-lab questions you won't be able to do until we finish this last little bit. So we'll just finish it on Wednesday. Wednesday we're gonna finish talking about what's left of this chapter, and then time depending, we could do some reviewing of some of the topics and stuff like that if you have any type of questions. But we still have this is one little last part about some calculations, and then that'll be it. Other questions on that? Okay. So the final will be, again, like I said, I believe it's scheduled from a week from this coming Wednesday. Just to give everybody a heads up in terms of the final, it is going to be a little bit different than the exams that we've been doing. There will be proctoring that will be happening with the final exam, not today's, but with the final exam, just to make sure everything's, on the up and up with the final. And that's going to require you to, on the final exam day, log into Zoom, and you are going to need your camera on so I could watch you kind of taking your final, just to make sure everything's good, in fairness for everybody. Everything's on the up and up for the final exam and all that good stuff. So just to give you a heads up, you got a week and a half. You do need to make sure that, you do have a camera accessible, which I think for everybody, which I can see here, looks like that ability is available. So you will have to log into Zoom for the final exam, and you will have to have your camera on, and it will be proctored that way for the final exam. For today's, you don't have to worry about it since it was sort of last minute the way they wanted that to be done. So we're going to do today just like we've been doing. And again, you got to sign the academic honesty agreement, all that good stuff. But for the final exam, 1 week from Wednesday, you will have to log on to a Zoom session for the final, and you will have to have your camera on while you're taking the exam, just so you know. Any questions on that? The final exam will include all the chapters, yeah. So it'll be comprehensive over the whole thing. It'll probably, if you think about all of our old exams, the big sort of calculations and stuff that we've done, will come back and probably find its way onto the final and stuff like that. So including obviously this chapter, which is obviously not part of today's exam. Some stuff from this chapter will be on there as well, but it will cover everything, all the stuff that we covered the entire semester. And again, you will need to have a camera accessible and on, and log into Zoom during the final exam time. I believe you should be. I don't think I've unpublished any of it, so I think you should still be able to access them and stuff like that. It won't be the same questions, obviously, and stuff like that, but you should, I believe, have some access to those exams. Just like you were able to review them after they're graded, you could go the same way. I believe they should still be there. I don't think I hit anything different. Any other questions on that? Okay, so everybody clear on the final 1 week from Wednesday. Again, you need to log into Zoom. You need to have your camera on, and it will be proctored. I'll be observing everybody as they're taking the final. And again, and remember, it starts a little bit earlier. I think I want to say 10 o'clock seems like the number I have in my head. So we'll start it at 10 o'clock, and you could take it at that point. So we have one more day to go in terms of lecture. I have no idea. I haven't even written it. I have like 6 exams before I even get to your final. So I got the 2 done for today. So I thought that was pretty good. So I got a few more to go. Whatever it says on the syllabus is what time it would be. I thought it was maybe 10, but you could be correct. 10:30 sounds good. So yeah, so whatever time it says on the syllabus is when we're going to take it at our normally scheduled time, just like we were in person face-to-face. And just like if we were in person face-to-face, you'll need that camera on so I could observe you as you're taking the final. Any other questions on any of that stuff? Okay, so for today's exam, again, we'll run like normal. So we'll do the honesty system here for sure. Again, reminder, there are different questions and versions. Make sure you upload that work in the 30-minute period after you submit your exam. If you need any help on anything, you can email me through Canvas, but I believe everything should be pretty self-explanatory at this point. Make sure, again, you follow the instructions for each of the individual questions on how to correctly sort of incorporate them. And a reminder that the score that you see at the end, again, may not be your final score until I've had a chance to obviously go through it and, make any appropriate corrections based on how the computer graded it. You do need to go through each of the steps. So again, you'll have to read the policy, sign the policy. That will open up the exam. Remember that once you start the timer, it is not going to stop, so you got to finish and all that good stuff. Today's exam is, like we said, only 14, 15, and 16. That is correct. And I believe all the information that you need for those should be in the conversions that you'll find at the top of the exam. And the periodic table will be there as well. And like usual, you'll be able to see all the questions at once, and make sure you only submit the exam once after you've answered all the questions. Any other questions or anything like that? Okay, so there'll be an announcement about 12 that the exam will open up about 12 and be available for you. And other than that, yes. Okay, it's not available anymore. Yeah, I'll try to go back. I'll try to go back and click those buttons to make the homework available. That's the problem. If I don't do it the next day or so, just send me an email to remind me, okay? But I'll try to go back and open those back up for practice. All right, anything else? All right, good luck on your exam. Again, I'll see you again on Wednesday. Obviously, there's no lab lecture today. Just go take the exam. Start it at 12 like you're supposed to. Again, I can monitor right when you started and all that kind of stuff. So make sure you do start it at 12. You should be in fine shape. And like I said, on Wednesday, we'll finish up the semester in terms of lecturing and stuff like that. All right, good luck. Have a good rest of your day. I'll see you on Wednesday. Good luck on your exam.